So once we have introduced the main algorithms appearing in the landscape of quantum computing, I would like to say that in parallel to this whole work devoted to finding speedups and quantum advantage by means of quantum circuits, there were a different trend, which is called quantum annealing, okay, focused on solving optimization problems, okay, also by means of taking advantage of the way quantum systems work. This is not a gate-based approach, okay, this is not based on quantum circuits, it's a different paradigm, but still it works for solving problems that might not be able to be tackled with classical devices. Here we can see an example of the things we do in multiverse computing, which is finding ground states, okay, global minimums of certain functions that are really useful for industrial applications. Since we know that quantum circuits are still far from our reach, in the sense that we need a lot of quantum gates, we need somehow a complex connectivity between qubits to perform as we want, okay, we have managed to create a different way of solving certain problems, okay, and this is quantum annealing. So some types of problems that you can find in this area is the so-called traveling salesman problem, okay, where you have a list of cities and distances between cities, okay, and you want to find the shortest route to go through every single city, okay, you want to visit and return to your origin, okay, by taking the let's say fewest number of, okay. A different example, when you want to minimize traffic jams, okay, in a city, when you want to find the lowest energy configuration of a certain material, okay, this is very useful for quantum chemistry, for drugs discovery, and so on, okay, when you want to even to simulate certain behaviors, okay, of certain molecules. Also for protein folding, okay, for medicine, for portfolio optimization. This is the way multiverse computing started, okay, when you have a certain portfolio full of assets, okay, and you want to maximize your profit and minimize your risk, you have to perform difficult computations, okay, because of the relationship between assets and the way they behave in time, okay, and this can be mapped to a certain function to be solved by means of quantum annealing, okay. So the idea behind this is that, well, if you have an optimization problem, okay, and you want to find the minimum, okay, energy state, that problem, what you can do is map your optimization problem to a certain Hamiltonian describing a physical system and find the ground state of that physical system. Okay, so that if you configure your problem in a clever way, you will only have to take care of the actual physical device, okay, which is driven to its ground state, which gives you the optimum configuration for your problem. Okay, that's a mapping. Sometimes you can achieve that, and sometimes you cannot. It is problem dependent. Okay, for the case of quantum annealing, because as you see on the screen, it is not universal, what means that you cannot really tackle every single problem, but you can really get good results for a certain bunch of. This is based on something called Adiabatic quantum computation, okay, which is the quantum universal example of this quantum annealing, let's say, sub-brand fit, okay. One characteristic example of quantum annealing, putting numbers in it, is finding the configuration, the optimum configuration for a function, okay, certain function plus a constraint. Here we have, for example, the set of configurations, okay, satisfying the function in there, which is x1 plus x2 plus x3 equal to 1. Okay, we know already, because it is a very simple example, that there are 3 cases satisfying this constraint when you only can have 0 and 1 for its variable, okay, which is 0, 0, 1, 0, 1, 0, and 1, 0, 0. Okay, so what you can do in order to adapt the problem for quantum annealing is basically transforming this problem into a function, okay, a quadratic function in there. And once you can develop or can extend your function, perform the map to a certain Hamiltonian, okay, which corresponds to an actual physical system, okay, behaving in an equal manner, okay, to your initial optimization problem. In this case, you can see that this function in there corresponds to a Hamiltonian of a quantumizing model, okay? And there are many, many examples of optimization problems that can be mapped to the Ising model, okay? This is like a very common way of tackling problems in quantum annealing, okay? So this all is based on the so-called adiabatic quantum computation, okay? The idea behind this is that we can interpolate adiabatically between a Hamiltonian whose ground state is easy to prepare, okay, the one on the left. You see that this is a convex function, very easy to model and so on, and a Hamiltonian whose ground state codifies the solution to my problem. As I was saying, we have a certain optimization problem, okay, and it is mapped to, let's say, for example, a chain of so-called Ising model, or a 2D Heisenberg model, whatever, okay, that encodes my problem. And my main goal there is to find the ground state of such a system, because it will be mapped to the solution of my optimization problem. Okay. One more example is the exact cover, which is the problem in which I have a space of solutions, okay, and some subspaces inside this space, and I want to cover the whole space by means of adding up some subspaces of it, okay, in such a way that I can certainly, let's say that, yeah, you can, as the name points out, you can really cover the whole space by means of just a few members of this space, okay? This is a problem that is super difficult to solve. It's NP complete, okay? So classically cannot be solved, okay? And even though there are certain, let's say, boundaries, complexities behind, okay, as if it scales quadratically or exponentially, many hyperparameters describing the problem and so on, it can be mapped to a quantum annealer, okay? So as I was saying, there exists this paradigm called quantum adiabatic computing, okay? But the actual tools that we have today, the ones that can be implemented in actual quantum devices, okay, is not that specific model, but quantum annealing, okay, which is the non-ideal implementation of adiabatic quantum computing. Why is it non-ideal? Well, because it works at finite temperature, okay, in such a way that, well, this pure state, this ground state of the initial Hamiltonian that was very easy to find, okay, now will be a mixed state, so that we will not certainly know what state we are working with, okay? It will be a superposition of states, because there will be some noise coming out from the environment, okay? Also, the interpolation between the initial Hamiltonian and the final one, the one that encodes our solution, will not be optimal, okay? And on top of that, this whole mapping from one Hamiltonian to the other one will be slow, but will be non-adiabatic, okay? So the way to achieve the good solution will be by means of sampling, okay? We will sample the outcomes of our algorithm and choose the best of our solutions, okay? Probably we will be stuck at some local minimum, okay, but it will be very close to the ground minimum of the optimization problem. And why is this faster than a classical approach, okay, such as simulated annealing, where you, instead of having a quantum system, you try to simulate that by means of noise introduced with thermal fluctuations, because when you work at that level with classical systems, you cannot really perform what is called quantum tunneling, okay? Going through certain potential wells by means of, as you all know, quantum physics, quantum tunneling, instead of having to climb up the well in which you are stuck, okay? You can really go through the mountain without having to climb, okay? And that's an advantage coming from the quantum side of the algorithm. Again, we find a quantum advantage, okay, in the sense that we can perform something that we could not with classical solvers, okay? These type of problems are called CUBOs, okay, quadratic and constrained binary optimization problems. Okay, quadratic in the sense that the highest power of the variables is 2, okay, we have no constraints applied to the variables, okay, we have variables that are bits, either 0 or 1, and optimization because we are basically minimizing or maximizing an objective function, okay? This is another example of how to go from a certain function to a certain Hamiltonian representing a physical system, okay? On top of that, yeah, we have many works devoted to the complexity of CUBOs, okay, as well as, well, the complexity of quantum algorithms. We have extensions of these algorithms by including constraints, by moving on to certain implementations that can be achieved with actual quantum hardware. And I think that this is a very powerful tool to apply for industrial cases. Okay, this quantum annealing thing.